Hey, dear class, in this section we're going to look at the special case of sum difference formula when the angle, the alpha, beta are equal. So what I mean by that is, this was an example of what we saw in the last section, cosine alpha plus cosine beta. Remember, it's cosine cosine, sine sine, all right? Think of that. And then because it's plus in here, we're going to be subtracting, and then it's alpha, beta, alpha, beta, right? Well, what if they're the same angle? What if it's cosine of theta plus theta? The same exact angle both times. Well, this becomes cosine theta times cosine theta, and this is a minus, and this is a sine alpha times sine alpha. It's the same same angle both times. I'm sorry, sine theta, sine theta. This is cosine squared theta minus sine squared theta. And that's where these formulas you're going to see come from. And since this is theta and theta, we just say that that's the cosine of 2 theta. And that's what we mean by a double angle. It's the same angle both times. And these formulas that we're going to see come straight from either the sum or difference formula, the sum formulas, from sine, cosine, tangent, all those different things that we saw in the previous set of notes. So there are those double angles. We have just the one for the sine of the double angle, 2 sine theta cosine theta. But for cosine we have three different forms, just depending on which one is the most convenient for the application that we're using it for. And notice the first one there, that is the one I just showed you on that first slide, that came directly from the sum formula for the cosine function. That has cosines and sines in its expansion, but the others just have sines or just have cosines. So there's times where maybe we want both, a sine and a cosine. So we would use the second equation there. There may be times when we only want sines or only want cosines, and we'd pick either the third or fourth. All right, now when we are using a double angle, it's because we are given some information about the original angle. So if you look here, we are between pi over 2 and 90 degrees. Pi over 2 and pi radians. So that's quadrant 2. If we double those angles, we could land in quadrant 3, or we could land in quadrant 4. It just depends on what angles we double. What I mean by that is if you give me like 120 degrees, if I double that, I would be at 240 degrees. I'd be at somewhere around here in quadrant 3 still. So there's theta twice, and 2 theta. But if I was started off at something like 150 degrees, which is still in quadrant 2, and then doubled that, I'd be here at 300 degrees, and now I'd be in quadrant 4. So being in quadrant 2 doesn't tell us the whole story, or what quadrant we're going to land in when we double the angle. But knowing what the value of one of the trig functions is for the original function will be that, and knowing where we started will give us all we need to begin unlocking which quadrant we land in. All right, sine of 2 theta is 2 sine theta cosine theta. All right, I know sine theta is 5/6. All right, cosine theta I can get from the square root of 1 minus 5/6 squared. That's just the Pythagorean identity. Remember, this is plus or minus depending on where we land. 5 squared is 25, 6 squared is 36, right? And then 1 minus 25/36 is 11/36. Right? 11 is not a perfect square, but 36 is, and let me keep my plus minus. So I have plus and minus the square root of 11 over 6. Now, which one is it? Well, we're in quadrant 2. So cosine is negative in quadrant 2. So it would be the negative square root of 11 over 6. So I can reduce that 2 and that 6 to a 3, and then 5 times the negative square root of 11, and 3 times 6 is 18. So there's the value of sine. Again, we know we're going to end up in quadrant 3 or 4. Sine's going to be negative in both of those. Cosine's going to tell the story. Do we land in quadrant 3 or do we land in quadrant 4? All right, which one should I use? I have 3 different versions of the cosine. Well, I'm going to use the one that uses sine because it says sine of theta is 5/6. So I can use this version right here, even if I never figured out what the cosine of theta was. I don't need the cosine of theta for that version of the double angle cosine. All right, and then same thing as before, the 2 and the 36 were reduced to an 18. I have 1 minus 25 over 18. That's 18 over 18 minus 25 over 18. That's negative 7/18. So cosine is also negative. That means we stayed, when we doubled the angle, we stayed in quadrant 3. We didn't make it into quadrant 4. Alright, so cosine's negative, sine's negative, so we are still in quadrant 3. Alright, this one asks us to develop a formula for the tangent 2 theta in terms of tangent theta, and then take a step further and go sine 3 theta in terms of sine and cosine of 1 theta. Alright, so we can do the same thing that we did before to derive the double angle formula for cosine when we started the video. I can just replace alpha and beta in the tangents, the sum formula for tangent, with theta, and you can see I get a 2 tangent theta up top and a 1 minus tangent squared theta down the denominator. So there is a double angle tangent formula. Right, to do the same thing as for sine, we can start off with 2 theta plus theta, right, and then split that up using the sum formula. So we got sines and cosines there, but remember the sine of 2 theta and the cosine of 2 theta, we just saw the formulas for those. So we can split that up. The sine of 2 theta is now 2 sine theta cosine theta. The cosine of 2 theta, I can write it as cosine squared minus sine squared theta. And then those get multiplied by the cosines and the sines. And that gives me a 2 sine theta cosine squared theta plus, that's coming from here, just multiplying the cosines together. And then here, if I distribute through, I have a sine times a cosine squared. So I get another one right here. And then a sine times a sine squared is a sine cubed. So we end up with 3 sine theta cosine squared theta minus the sine cubed theta. Alright, if you look here, we've got sine squared, cosine squared, tangent squared, and we've got them written as non-squared trig functions. A lot of times these are called the power reducing formulas, where we go from squared trig functions to non-squared trig functions. Alright, pay close attention to the sines, the cosines. The sine squared theta has a minus right here, and the cosine squared theta has a plus. Alright, where are these coming from? Well, they're coming directly from these two right here. If I isolate the sine squared, notice I have, I'd move a 1 over, so I'd have a cosine 2 theta minus 1, and then I have a negative 2 sine. So if I divide away the negative 2, these will switch around and become positive and cancel with that 2 on the bottom. This will be a 1 minus cosine 2 theta over 2 equals sine squared. So this is, they're coming from these two double angle formulas for cosine. And then the bottom one, the tangent squared, is just sine squared divided by cosine squared. So this, basically think of that as a fraction there. So what do? I flip and multiply, and when I flip and multiply, I get the 2 up top, the 1 plus cosine 2 theta on the bottom, the 2's cancel, and we end up with this formula. All right, so it's the double angle formulas for cosine, isolated for sine squared and cosine squared, and then we divide to get tangent squared. You got to remember, you're not going to have access to these. You're expected to know all of these. All right, that's a college rule. That's not my rule. That's a college rule. And you want to memorize as few things as possible. So if you can memorize these double angle formulas for cosine, which again, we started the video off showing that I could get the double angle formulas for cosine from the sum formula for cosine. You don't have to memorize any of these. You could derive them on demand. All right, write an expression for cosine to the 4th that does not involve any powers of sine or cosine greater than 1. Again, power reducing. So if I'm supposed to reduce my powers from 4 down to 1, I'm going to use that cosine squared formula a couple of times. Now watch what happens. This is cosine to the 4th. Cosine squared is equal to this. So if I square both sides of this expression, I would have cosine to the 4th. And now expanding that, you got to square it out. 1 squared would be 1. Outside would be 1 times cosine 2 theta. Inside would also be 1 plus cosine 2 theta. So again, what I'm doing here is I'm squaring this. Foiling that out, I get 1 times 1 is this 1 right here. Outside, 1 times the cosine 2 theta. Inside is the cosine 2 theta times 1. It's 2 cosine 2 thetas. And then finally, last, I'd have a cosine times a cosine. That's cosine squared 2 theta. So I'm just foiling that numerator, and then squaring the 2 on the bottom gives me 4. That's where this 4 right here is coming from. So all you're doing here is just writing cosine to the 4th as cosine squared squared, and then you're squaring this expression that comes from the power reducing formula for cosine. All right, but look, can't use anything greater than 1. This is greater than 1, so I need to apply it again there. So cosine squared 2 theta is 1 plus double that angle. So the angle is 2 theta, so I'm doubling it. So I end up with a 4 theta inside that expression. So that's how we tackle using the power formula, the power reducing formula multiple times. All right, notice on this one, solving this equation, sine theta, cosine theta. If they're equal to 0, I could say sine is equal to 0 or cosine is equal to 0. But when they're equal to something like -1/4, when it's not 0, I can't say anything definitive about what sine and cosine can be. So I'm not in a position where I can solve this yet. But if I use a double angle formula, this is almost 2 sine theta cosine theta, which would be the sine of 2 theta. If it were 2 sine theta cosine theta, but it wasn't. Well, I can fix it by multiplying both sides by 2. So multiply by 2 to get it to look like the double angle formula. And now this is sine 2 theta, but over here the 2 and the 4 will reduce, and this will be equal to -1/2. So when we see something that's close to one of these formulas that we know, we can manipulate it to finish it off as long as it involves scaling it up with multiplication or dividing. All right, and then once we have it in that form, we just set the inside, 2 theta, equal to what angles on the unit circle between 0 and 2 pi create the sine being equal to -1/2. So 11 pi over 6 is one of them. Another one is 7 pi over 6. All right, we'll look at the 11 pi over 6 case. So the thing inside, okay, this thing inside that's our double angle is equal to 11 pi over 6 plus, again, 2 pi k. This is just the fact that we can just keep going around the circle over and over and get back to where we started as many times as we want to. So if I divide both sides by 2, I get 11 pi over 12 plus pi times k. And that means I can add pi or subtract pi as many times as I want to. Right, we just want to make sure that we don't go over 2 pi. Right, because 7 pi over 6 also works, we would do the exact same thing for 7 pi over 6. Right, and then we find from all this list of possibilities, what are the ones that are in the 0 to 2 pi range. So there's the 4 that ended up being in there. All right, this is a very common thing that you see in like an elementary, like first semester physics problem. This double angle formula that tells us how far the range is based on an angle of elevation that we fire a cannon or some projectile. And it has a double angle in it. And if you do the math, and we want to find where it's a maximum, we're going to replace that sine 2 theta with 2 sine theta cosine theta. So there's our range formula. Again, all I did there is just replace this with 2 sine theta cosine theta. And then because there's a 2 here and a 32 here, we reduce that to a 1 over 16. So that's where that's coming from. But when we use that original, if this is the range, well, the sine function goes between -1 and +1. And since the negatives aren't possible, we're not going to do negatives. We're going to make it 0 because it's got to be a range. It doesn't make sense for it to be a negative range. That happens when the angle is 0 degrees, right? And this happens when we have 90 degrees, when sine is 90. Anything between there, you get a value that's less than 1, bigger than 0, like a half, you're going to make this smaller. So that this is maximized when we have 1, which means that 2 theta would have to be equal to 90, which means theta is 45 degrees. That's the way that you can work that out. All right, looking at our power reducing formulas that we saw a little bit earlier, if we replace theta, the angle that we're given that ends up being doubled, so there's an angle we're given, we double it over here. If we replace that with half of an angle, so like alpha over 2, well, what happens when you double alpha over 2? You would just get alpha. And the same thing goes in the cosine function. If I had an alpha over 2, when I double that, I would just get alpha. And so these are what we refer to as the half angle formulas. Once we take these square roots, we'll have the sine, cosine, and tangent of half of an angle. And we get plus or minus the square root of these different things. All right, the sine is determined by the quadrant that we end up in. Okay, so again, if I start off at an angle of 300 degrees, well, half of that would be 150 degrees, like right there somewhere. And I'd be in quadrant 3. right? But if my angle started off at like 240 degrees, half of that would be 120. I'd still be in quadrant 3. So it all depends on where we start. Did I start here at like 210? Half that would be 105 degrees. So the half angle formula depends on, like the sine of the half angle depends on where does the y coordinate end up when I split the angle in half. All right, if I want to use the half angle formula, all right, 75 degrees is a half of 150. So alpha here would be 150. So that alpha right there would be 150. And the cosine of 150 degrees, if you look at your unit circle, is the square root of 3 over 2. So I have 1 minus the square root of 3 over 2. Simplifying, I can multiply the top and bottom of this expression by 2. Right? Inside the radical, that will give me 2. Square root of 3 over 2 times 2, the 2's will cancel and give me just the square root of 3, and then 2 times 2 is 4. All right, now the square root of 4 is a perfect square, so we can bring a 2 out of that. But the 2 minus the square root of 3, that's not a perfect square, so I just leave that underneath the radical. And notice with this formula, with the half angle formulas, it's very common to see things like a square root of 3 underneath a radical a second time, like the square root of a square root. It's very common to see that. I will also want to find the sine of negative 75 degrees, so we can start off by using the odd powers for sine. All right, and now we're going to apply our half angle formula. So it's the opposite of the sine of 150 over 2. So we, again, plug in our value here. Again, why is this negative? It's because a negative 75 degree angle would go this way. So down this direction, 75 degrees. And the sine is the y coordinate. And since I'm down below the x-axis, I end up with a negative value. So that's why I got this negative number down there. And it's also the odd powers of sine. All right, cosine of 150 is square root of 3 over 2, just like with that last problem. So we end up when we multiply top and bottom by 2 to get rid of the fraction within the fraction, we end up with 2 plus the square root of 3 in the numerator this time, 4 in the denominator. And once again, we can't simplify that. The square root of 2 plus the square root of 3, the 2 plus the square root of 3 under the radical just remains under the radical. All right, and then as to be expected when you have a new formula, like half angle, double angle, sum difference, you're going to have these questions where they give you one of the trig functions output, they give you what quadrant you're in. This is quadrant 3, and we got to find the sine of alpha over 2, cosine alpha over 2, tangent alpha over 2. So we're using, again, those half angle formulas. So I plug in 1 minus cosine alpha over 2 underneath the radical. The cosine is negative 2/3, so I get 1 plus 2/3, right, which is 5/3 over 2. That's 5/6, so we get the square root of 5/6. You can rationalize that. This is just, let me show you where that's coming from. The square root of 5, 6 can be split up into the square root of 5 times the square root of 6, and then we multiply top and bottom by the square root of 6. All right, the square root of 6 times itself is 6, and then we have that 5 square root of 6 on the top. This should have a square root of 5 right there, like that. All right, the square root of 5 times 6 is the square root of 30, which is the square root of 30 over 6. That's an error on your PowerPoint there. That should be a square root of 5 times the square root of 6, not 5/6. All right, same thing for cosine. We're going to just replace that in there, 1 plus cosine alpha, so cosine is negative 2/3 again. We split that up, we get 1/6. The square root of 1 is 1, square root of 6. So once again, we have negative 1, the square root of 1 over the square root of 6. Just splitting this up. All right, that is 1 over the square root of 6, and then just rationalizing. Square root of 6 on the top, square root of 6 on the bottom. So square root of 6 times itself is 6. Negative 1 times the square root of 6 is negative square root of 6. All right, then I can just take those two values, all right, that I got from the last two problems, and divide. I don't need to start over like they did here. On this one, I got the square root of 5. I should have written it like that. The square root of 5 over the square root of 6. That was one of the steps I had. The square root of 5 on top, the square root of 6 on the bottom. And this one I ended up with the square root of 6 on top, the square root of 6 on the bottom. I could just divide these two. All right, flip multiply, square root of 6 cancel, I get negative square root of 5. So you can do it that way, you can do it the way it shows on the PowerPoint. But remember, tangent's always sine divided by cosine. So if we've already calculated sine and cosine, then just divide them and you have the tangent. All right, and then there's some alternative versions of the half angle tangent formula that don't involve the radicals. And sometimes those are definitely beneficial if you don't want to deal with radicals in a problem.